All right, let's dive into one of the coolest, most fundamental links in all of physics. We're talking about the deep, invisible, and honestly, kind of shocking connection between electricity and magnetism.
I mean, think about it. What could possibly connect a massive, chaotic blast of energy, like a lightning bolt, with a tiny, delicate compass needle that just wants to point north? They seem like they're from completely different worlds. But what if I told you they're actually two sides of the very same coin?
You know, the story of how we first figured this all out, it doesn't start with some genius having a brilliant idea. Nope, it starts with a total, complete accident.
So picture this. It's 1820. Hans Christian Ørsted is in the middle of a lecture. His desk is a cluttered mess of wires and gadgets. He flips a switch to send a current through a wire for his demonstration, and out of the corner of his eye, he sees a compass needle, which had nothing to do with his experiment, suddenly twitch, just for a second. That little twitch was everything. He realized the electricity flowing through the wire had to be creating some kind of invisible magnetic force.
Now here's the absolute key takeaway from that. A single lonely electric charge just sitting there, well, it doesn't do much. But the second you get those charges moving, the second you create an electric current, an invisible magnetic field just springs into existence around it. That was it. The first real proof that these two forces were secretly connected.
Okay, so this invisible field exists, but it isn't just chaos. It actually follows a very specific, almost predictable set of rules, which of course brings up the next big question.
Right? If a current in a wire makes a magnetic field, how on earth do we know which way it's pointing? Is it going up? Down? To the left? How do you figure that out?
Well, luckily, there's this super simple, almost ridiculously easy trick for it. It's called the right-hand thumb rule. Seriously, you can do it right now. Just take your right hand, point your thumb in the direction the electric current is flowing, and look at how your fingers naturally curl around. That curl, that's the direction of the magnetic field. It's that simple.
Now, trying to show this 3D wrapping on a flat 2D screen is tricky, so physicists came up with a clever shorthand. Think of an arrow. If the magnetic field is coming straight out of the screen towards you, you'd see the pointy tip of the arrow, right? So we draw a dot. If it's going away from you into the screen, you'd see the feathers on the tail. So we draw a cross. Dot and cross. Simple. So, a current makes a field. But what happens when another moving charge flies into that field? Well, it feels a push, a force. We call this, you guessed it, the magnetic force. And how strong that push is depends on just three things: how much charge it has, how fast it's going, and of course, how strong the magnetic field is.
But here's the thing about this force. It's picky. It's really picky. It doesn't just act on any old charge that comes along. It has this very specific set of conditions that have to be met before it'll even lift a finger.
And its demands are kind of weird. First off, if a charge is just sitting still, the magnetic force completely ignores it, doesn't care. Second, if the charge is moving perfectly in line with the magnetic field, either with it or against it, again, nothing happens. It only acts when a charge cuts across its field lines. And third, when it does finally act, it always pushes at a perfect right angle to the direction the charge is moving. This means it can never speed a particle up or slow it down. All it can do is change its direction. It's a pure turning force.
Now, these quirky, specific rules might sound a little abstract, but they are the absolute key to how we harness this force to make basically everything in our modern world run.
Let's put these rules to work. Imagine you've got a simple rectangular loop of wire, and you place it in a magnetic field. Now you send a current through it. The current flows up one side of the loop and down the other. So based on our rules, the magnetic force is going to push one side of that loop up and the other side down.
So what happens when you push up on one side of something and down on the other? It spins. That twisting, turning force has a name. It's called torque. And that one simple idea, that torque, is the bedrock of how we use electromagnetism to create motion.
And I'm not just talking about some lab experiment. This is it. This is the core principle behind every single electric motor, from the one in your blender to the ones that power electric cars. It's also how we can use this effect to measure electricity itself.
A galvanometer is the perfect example. You run a current through a little coil of wire. That magnetic torque we just talked about tries to twist the coil, but there's a little spring fighting back. So the more current you have, the stronger the magnetic twist, and the farther it can push the needle against the spring.
It's such a beautifully simple and elegant way to see and measure an invisible current.
So we've got the concept, we've got the weird rules, and we've got the real-world applications. But how do scientists and engineers calculate all this stuff with precision? Well, for that, you need the master code.
It has a fancy name, the Biot-Savart law. Now, don't worry about the math, it can get a little hairy. The big idea here is that this law is the ultimate tool. It doesn't matter if your wire is a straight line, a perfect circle, or some crazy tangled mess. This one law lets you calculate the exact strength and direction of the magnetic field it creates at any single point in space. It's the whole shebang.
And all of this brings us back to the single most important point of this entire explainer. Electricity and magnetism, they're not two different forces. They are two faces of one single, fundamental force of the universe, electromagnetism. And the bridge, the thing that transforms one into the other, is nothing more than a moving electric charge. That's the secret.
So that leaves us with one final huge question. We've just seen very clearly how moving electricity can create magnetism. But does it work the other way around? Can you take a magnet and use it to create electricity? Well, that is a story for another time.